And it's a pleasure to be here again. I want to talk to you about some of the things that many of you are already familiar with, and I thought it was important to just discuss it. So I am going to talk about aptamer structures, but I'll begin with the primary structures, also known as sequences. We all begin with this large collection of fully randomized molecules, 10 to the 13, 14, 15 molecules, and we work pretty hard to prune it down to something a lot smaller. Let's call it 100,000. There's a wealth of information there. I think we all know this. The reason these sequences are there because they're functionally related. And if we all manage to align those sequences correctly, we can learn. This almost always requires that we put in gaps someplace. And these sequence families that emerge are really families because they share a functional property for which they were selected. So in a sense, magic happens from starting libraries to fully enriched groups. When you manage to align these properly, you get variations on the theme that if you didn't look at that, you would then have to ask those questions by making synthetic variants. But in many cases, they're already there. And so some of the features of these conserved motifs, they're typically short. They often occur in different regions in the random region, and they're often circularly primitive. Just maybe a mundane suggestion is use of non-proportional fonts where we align the sequences is in fact really useful. Courier is an example. It's now widely considered to be medieval, and yet things like this are quite useful. With NGS now, what we used to be confined to maybe 50 to 100 sequences, we can now look at 10,000. So there's a massive amount of information that we can all benefit from this kind of analysis. So I knew I would be speaking after Philip Johnson. And so these are Johnson will be a lovely three-way helix junction motif. And the one that I chose for the purpose of illustrating this is a three-way helix junction motif that we identified from one of our PGF-DB aptamers. We identified a number of years ago. So DNA-based aptamer. And what we have here is you see my cursor on screen? Yeah. Great. So is distinct helices 1, 2, and 3. And getting to that required alignment of a type that puts in gaps and identifies them when you do it correctly, sequences that are conserved. So let me just point your attention to helix 3, which is shown right here in the middle. So if you look at the positions in this helix, they're close to the helix junction. And these three-way helix junctions require that you have unpaired nucleotides at the point of strand exchanges to make the geometry. So let's just walk down the group list. There's an AT, you go down, it's an AT, it's an AT, it's always an AT. So here it is, conserved. But then as you go one position outside toward the periphery of the helix 3, you see it's generally a TA base pair, but in some cases, it's actually a stitching. So it's a pyrimidine purine sort of a base pair. And this theme is basically common as you go along the helices. What's conserved is in the middle, but then as long as you have a base pair, you're okay. So this is the kind of circular permutation that really gives you confidence that you've gotten the folding correctly. And what is useful to recall is that this very kind of analysis was used to solve the secondary structure of ribosomal RNA, which is considerably bigger than the little aptamers that we tend to deal with. So this is a powerful tool that we already have. They're there for us to investigate. It tends to be underutilized, and so this is an invitation for all of us to take advantage of what's already in front of us all the time. Now, staying with STEAM, it so happens that we identified this cross-link between one of the nucleotides at the strand of exchange. This region is highly conserved, which interacts with phenylalanine 84 on PGFBP. We made this model between the aptamer and the crystal structure of PGFB to show this interaction is at the receptor binding site. So you can obviously do post-Lex modifications, which we have done in order to improve the stability of this particular DNA-based aptamer by putting in 2' fluoro or 2' O-methyl substitutions where we could. And it's clearly not everywhere that we can do this, but maybe the more interesting point to make here is, just like Philip has shown you, we decided to make a controlled sequence that has the same secondary structure as the active molecule by simply inverting base pairs at the point of exchange. And this completely wrecks high affinity binding. So rather than using a scrambled sequence that may have the same composition, it's sometimes useful to actually introduce mutations where you at least preserve the secondary structure. So would I like to unmute? No, I would not. So you guys all know this. See 2' endo for DNA and DNA-like, C3' endo for RNA. Here we go. So we looked at a bunch of co-crystal structures between aptamers and protein complexes, and this is a super busy table, but it's really easy to interpret in that when you have RNA or RNA-like aptamers, things tend to be primarily C3' endo or C3' endo-like. DNA tend to be C2' endo. The point of this is that when you begin with RNA-like libraries, because RNA sugar pucker tends to refer to C3' endo, you can end up substituting a larger fraction of the ribonucleotides with either 2' fluoro or 2' O-methyl, because they have similar conformations. In DNA-based aptamers, far less so, because you have this disparity of the sugar pucker. I don't need to tell you guys now anything about this point. This is what you are well aware of every minute of every day. And what we have done is found a point in which we can introduce modifications, 5 positions pyrimidine away from hydrogen base. It does turn out that some of the favorite amino acids that are much more prevalent in antibodies, in antibody paratopes as they engage protein epitopes, are also giving us the best results in the context of nucleic acid-based lipids. And I'm now going to tell you a little bit about the 6 co-crystal structures of these modified aptamers that we have, or slow operating modified aptamers, so on as we call it, that we have solved to date and draw some conclusions from what we have done. But I'm going to begin with the linker itself. And I decided that this was important to me for this audience, primarily because I know that Gunther would be. This is a rigid point of contact between the side chain and the base. So you have these, three basically rotatable bonds. It's a glycosidic bond, but then you have these two other bonds that were, for convenience, calling tau and omega. And so it turns out that this does make at least the ambient bond coplanar with base. When we do see deviation from coplanarity, it's generally because there is an interaction either intra or intermolecular interaction with something else that drives us away from coplanarity. But clearly not all possible rodimers are observed. And in fact, the one that is clearly the most preferred in this is this anti-carbonyl transaminate and anti-glycosidic bond. So the way I tend to draw these things, which is like this, is just it's never observed because there are other ones that are much more prevalent. The linker itself does participate in both intermolecular and intramolecular contexts, the same as you would expect in a protein-based. So now, moving on to some of the examples of co-crystalline structures in the PDGF-BB sonomer that you've seen a nice movie a minute ago. All 8 of the side chains actually directly contact the protein. This is a 2-domain structure that has a stem loop as well as a very small pseudomolecule. The next example is the MGF sonomer, which has a much more unusual structure in the sense that it's dominated by this triple base stacked center of this sonomer. But there's no helical character in this point. So these modifications do drive things to an under one helix. One motif that I want to draw attention to is this benzyl zipper, which does occur in the helix. On one of the modified helical aromatic side chain interacts with the adjacent base in a reciprocal manner. So you have a pseudo base pair where the hydrogen bond interaction takes place. The IL-6 sonomer is clearly a 2-domain structure where you get the interaction of the stem loop and the G quartet domain, basically making the sort of bare part of the protein itself. The two can be disconnected, and it's pretty clear that the G quartet domain contributes the most in terms of binding. Now, I'm going to tell you a little bit about this next example, which is a fen-propyl modified library. We decided to test this modification with the intent of penetrating deeper binding pockets on the protein, thinking that this would be a good thing. The exact opposite thing has happened in that all except for 2 modified side chains ended up in this monstrous hydrophobic hole. That is clearly responsible for folding of this thing. And this is not just some accidental arrangement of these phenyl groups. There's clearly really nice edge to base and face to face stacking interactions. In the interest of time, so the next one is IL-1 alpha. This is one of the most tightly folded globular sonomers that we have. It has a slightly larger naphtho group, which also I draw your attention. There is another zipper motif, but in this case with a different side chain, so it's clearly a recurring theme. This particular structure has resolution that's less than 2 angstroms, and so you can see actually water molecule in this context. I'm going to skip this next one for the interest of time, and just show you, the length of these reagents when fully truncated, and the fact that there's a variable number of these hydrophobic aromatic side chains that interact with the protein, and then the ones that form internal motifs. And I'm going to basically conclude with this idea that was pioneered by Anna Pyle at Yale, who got frustrated with the fact that there's 6 rotatable bonds per monomer, which is why aptamers in general have a much larger conformational flexibility, but you can't really represent it all that easily. So instead, you can just bridge these and make these theta bonds, and then that allows you to represent the backbone the way you would with proteins with Ramachandran plots. And so we see here on the right, RNA has much more conformational flexibility. What's in the crosses, in the gray crosses, are the conformations that are particular for the helical geometry. And anything outside of that is something else. RNA is all kinds of stuff. DNA, this is naturally occurring DNA, primarily in helical conformations. But when you look at aptamers, you see not a whole lot of additional conformational flexibility for RNA-based compared to DNA-based aptamers. Now, the shape complementarity between atom and protein interactions tend to be as good as what we typically see with antibodies, and even more importantly, the epitope size, even though aptamers generally tend to be smaller than antibodies, tends to be quite. We have done some work with 2 modifications. The only thing I'm going to say about this, I know it's a complex slide, is that many of the single modifications in libraries, aside from the hydrophobic aromatic ones, are really not very good. Morpholino, not much different than DNA. Even tyrosine by itself is not all that great, but when you couple a tyrosine side chain, which is one of the most overrepresented amino acids in antibody CDRs, you get some of the best. And we do get much better nucleus resistance when you have this side chain. So I want to conclude with a notion that was discovered really by the FDA, is that aptamers are much better probes for subtle conformational changes in proteins than antibodies. And this is something that we can all take advantage of. There's some conclusions that I've mentioned most of these things, but I'll go to the questions in terms of aptamers being better probes of subtle conformational changes. It would be nice to understand why in the world that is, and we don't know at this point. And then finally, in the protein world, folding has been such a difficult problem for a long time, but now it seems like it's solved. How many structures do we need to get anywhere near that kind of success? And this too, we don't know, but it's important.